In this video, we'll discuss reflection and transmission. And I'm going to show the PowerPoint slide and we can discuss that. So even though these are for chords, we want to remember that in general this works for all different phenomena, whether it be water or some type of air pressure, pulses. This works for all those different types of medium. It's just easiest to show this with a chord. So the first instance here, we have a chord that has a fixed end. You see the little red peg on all of these. And as the pulse moves towards the right, it gets to this interface, which is a solid interface, and the chord will actually wrap and invert itself and go back in the opposite direction. And so this holding of the chord is what causes this flip to occur. Now there we have a demonstration of this with a fixed end, and you notice how it bends and inverts itself on the other side. Now the other possibility is having a free end, where this end is allowed to move, and when this happens, the wave pulse doesn't invert itself. It goes back in the same orientation as it was traveling to the right. And so these two different possibilities make the pulse do two different things. So let me show you the loose end. And you'll notice how this end pops up and just comes back down. And basically it acts like if you're over here to send the pulse, you'd have to whip the cord. This is just doing the same action, whipping the cord and sending it back. Now you can have a chord with two different sections, and so you have an interface here, and this interface you have a lighter section that connects to a heavier section. So as the pulse travels to the right, it comes to this connection. Well, the connection is neither fixed completely, and it's not really loose or free completely. So what happens is that the transmitted pulse will go in the same orientation, same upward pulse, but there will be some of the pulse that goes in the opposite direction back to the left. So in a sense, this acts like a semi-fixed point for this chord, and this is at the intersection boundary. Now the important thing is that the frequency in both chords is the same. If it wasn't, then the rope would break. And the amplitudes of the reflected and transmitted waves depends on the density difference, or the mu, the mass per length. We can look at this also in a simulation. And we're going to go from a thinner to a thicker chord. That's what the book shows. You can see how you get the warp on the thin side to get it to invert, and you get the transmitted that's in the same orientation. Now the frequency is going to be the same, but notice that the velocity is not. The velocity is faster in the thinner cord and slower in the thicker cord. Now the reason for that, it comes from this formula, V equals the square root of the force of tension divided by mu. The force of tension has to be constant across this whole string. So the force of tension is a constant, but mu changes. Mu is actually getting larger in the heavier cord, which means that if this mu is larger, then the velocity will decrease. So the velocity is slower on the heavier side. Now there's one other option in the notes that's not in there, but we can look at what happens when you go from a thicker to a thinner cord. And here you notice that you do get the transmitted wave, but both of them are in the same orientation. The wave or pulse on the thicker cord doesn't invert itself like it had with the thinner on the left-hand side. And notice too that your velocity is faster on the right-hand side with a thinner cord, for the same reasons that we talked about with the opposite type of cord. So this is the idea of reflection and transmission. The reflection is based on this boundary point, whether the wave reflects back in the same orientation or inverted, and the transmitted wave is what proceeds down after hitting this interface point.